My talk today will focus on the total relative sea level changes over the last 6 decades. What we call total relative sea level change is actually the sea level change that is experienced by people on the seaside when they are on the coast. It is the sum of the sea level change at the coast plus the vertical crustal motion of the coast itself. It gives what we call the relative sea level change, and it is actually what we want to estimate when we want to further assess the potential impacts of future sea level rise. In my presentation, I propose to proceed in 2 steps. In a first step, I will show you what we know about the sea level regional variability, the sea level change at the coast, and I will focus on a recent method which tried to collect all the information we have from tide gauge records, ocean models, and altimetry. And in the second step, I propose to show you how we can compute the vertical crustal motion of the coast itself, and to deduce for some places of interest the total relative sea level change over the last decade. So first, what do we know about the past sea level changes in the ocean? Thanks to satellite altimetry, we have a pretty clear view of the past sea level changes over the world over the past 2 decades. Satellite altimetry has indicated that there is a global sea level rise of 3.1 millimeter per year since 1993. And thanks to its global coverage, there is as well an important regional variability in sea level. There are places where sea level has risen at a pace which is 4 times faster than the global rise, like in the western tropical Pacific, and regions where it has hardly risen, even fall, like in the western coast of the United States. With tide gauge records, we have also a pretty clear view of the past global mean sea level rise since over the last 6 decades. They indicate a rise of 1.7 millimeter per year, as Guy have shown before. But we don't have information on the open ocean variability, as we will see later. So when we want to estimate the past sea level change, the past sea level changes at the different places of the world ocean, the problem remains the same. What was the regional variability over the last 6 decades? Was it different from what we're observing now? Or are these patterns we're observing now over the last 20 years, were they actually steady or did they change with time and space? We have already some insight on this question, actually. We know that over the last 20 years, the regional variability in sea level we're observing by satellite altimetry, that I've plotted here in terms of trends, is actually explained by the regional variability in thermal expansion. I've plotted here the thermospheric sea level from temperature and salinity data of the World Ocean Atlas, and you can see that the thermospheric sea level explains most of the regional variability in thermospheric sea level explain most of the regional variability in sea level over the past 20 years. This result has been confirmed by studies based on models with assimilation, like the models of Detlef Stammer and Wunsch, or models without assimilation in the study of Lombard and colleagues. Besides this result, we know that the patterns we observe in thermal expansion have changed with time and space in the past. We have indications, thanks to measurements in temperature and salinity, that the patterns over the last 6 decades in thermospheric sea level were significantly different to what we're observing today over the last 20 years. They have changed in response to the main climate modes of variability, such as ENSO or NAO. So it's very likely that these patterns we're observing now with satellite altimetry have changed as well in the past, over the last 6 decades. But the main question remains. We want to estimate the past sea level at regional scale, but we know that it has changed with time and space, and we don't know how to estimate it in the open ocean. The first option to get information on the past sea level at regional scale is to look at the few data we have back in the past. The information we have on sea level before altimetry era is based on tide gauge records. The problem with tide gauge records is that they give us sparse information, which is essentially located on coastal lines or on islands, like in the Western Pacific. This dataset cannot inform alone on the open ocean variability. Another option to find information on the past sea level regional variability is to look at models. Ocean models give in their output the sea level, over the last decades based on the sum of the thermospheric sea level plus the allospheric sea level and a small barotropic component. So it gives an estimation which has the advantage to be dynamically consistent and which takes the information either of the atmosphere when we have a forced model, like the Drakkar-Nemo model, or information of both atmosphere and measurements of temperature and salinity when we have a reanalysis, like the soda reanalysis. I've plotted here the sea level trends given by the Drakkar model over the last 5 decades here, because it starts in 1958, and here the sea level trends given by soda. One of the problems with models is that different models give different results. And we can have results which are fairly different between a model and another. I've plotted here the difference between the soda analysis and the Drakkar model in terms of trends. And you can see that the signal in the difference can reach up to 100% in some regions of the signal which is in each model. Models give interesting information because for many parts of the ocean, especially within the tropics, for example, they give fairly good results, in particular when we compare them with tide gauge records. I've compared here models with annual time series of long tide gauge records, and I've computed the correlation coefficient with the ORA-S4 reanalysis, which is the reanalysis of the ECMWF. You see that in the tropical Pacific, it gives good results with correlations up to 0.7, 0.8, even 0.9. But in other regions, we have results which are not that good, like particularly in the Indian Ocean here or some places of the Atlantic Ocean. Recently, a new method has been developed which gather both information from tide gauge records and information from altimetry or GCMs. What we call GCMs are ocean models. This method consists of extracting the spatial structures which are characteristic of the ocean sea level variability from 2D sea level grids like satellite altimetry or ocean models, and to use this information to interpolate backward in time long tide gauge records of high quality. It gives as an output a 2D sea level over the past 6 decades, for example. It has been extensively studied in the recent literature since 2000. I propose here to give you an overview of this method. And to give you an overview, I will present you 3 different reconstructions, which actually cover more or less what has been done in the last 10 years with this method of 2D sea level reconstruction. The 3 reconstructions are based on the same high-quality tide gauge record, shown here. We've used a data set of 91 tide gauge records that are corrected for the GIA effect. And each reconstruction is based on EOFs, which are computed from a different data set, 2D sea level grid, like here altimetry, in this case the Drakkar model, and in this case the solar model. In this case, when we use altimetry, we have the advantage when we want to compute the spatial structure of the ocean from this data set to have a data set which is very representative of the real state of the ocean sea level. But we have the drawback to have a fairly short data set, which covers only the last 20 years. We cannot be sure with this data set to catch the low-frequency spatial structures of the ocean that are at stake over the last 60 years and that are very important to interpolate backward in time the long tide gauge records, especially. For this reason, other methods have been developed which are using runs of ocean models, because the long runs are covering a longer period, so we may catch here with these runs the low spatial frequency structures of the ocean that are important to interpolate, especially backward in time, the long tide gauge records. But they are less representative of the real state of the ocean sea level than altimetry. Let's have a look to the results and the differences when we use different reconstructions. I've plotted here the sea level trends from the reconstruction based on altimetry on the left here, based on Drakkar here in the middle, and based on soda here. The 3 different reconstructions give fairly similar results in terms of amplitude in trends and broad scale patterns. I've plotted here the absolute difference between the trends from the reconstruction based on Drakkar and the trends from the reconstruction based on soda. You can see that the differences are lying between 0 and 1.5 to 2 millimeters per year. except in some located regions of high temporal variability, like the western boundary current regions, here in the Gulf Stream or the Crucio Stream, but there is also in the Malvinas confluence or the Agulhas current. In terms of reconstructed global mean sea level, they have the three different reconstructions are in fairly good agreement. They show the same trend over the period 1950-2010, a trend of 1.7 millimeter per year, which is consistent to the studies based on tide gauge records, corrected for land motion, like the study from Guy. But they show a slightly different internal variability. We have a fairly similar internal variability between the reconstruction based on altimetry and Drakkar, but the one based on SODA showed differences in terms of internal variability. In a recent study, we tried to find out what was the best reconstruction in order to have the best estimation of the past sea level changes. To do so, we need to compare the different reconstructions with independent tide gauge records. The point is that there is no that much tide gauge records which are independent in the past, and we used most of them in the reconstruction. I mean, most of the high-quality tide gauge records. So what we've done is simple. We took one of the tide gauge records from our 91 tide gauge dataset, and we removed it from the dataset. We performed a new reconstruction based on 90 tide gauge records only, and we compared this new reconstruction with the independent tide gauge record previously removed. It gives us 91 independent comparisons to evaluate the different reconstruction. I show here the correlation of the annual time series of the independent tide gauge records with the different reconstructions. And you have here the number of tide gauge records. You can see that the different reconstructions perform fairly well because they have correlation with the independent tide gauge records higher in general than 0.7. And surprisingly, they performed similarly. We didn't expect the altimetry reconstruction to perform as well as the model-based reconstruction because it's based on the short record, as I told you before, and we may miss here the low spatial frequency structures of the ocean. But actually, we interpret this result as some kind of compensation between a high-quality data set, which is very representative of the real state of the ocean, and long data set which catch the low-frequency spatial structure of the ocean. In a potential, it's hard to find a best reconstruction actually when we compare to independent records, tide gauge records. So in an attempt to improve the result, what we've done in this recent study is to compute an ensemble mean reconstruction based on the different reconstructions. So here it's the first attempt. We used the previous three reconstructions showed here, and we computed a mean reconstruction as the mean of the three previous reconstructions. The idea is to do exactly as what is done for climate studies. We expect, by computing the mean, to smooth out the different outliers of each reconstruction. And we expect to enhance the signal which is in agreement between the different reconstructions. I've plotted here the trend of this mean reconstruction, and I've plotted here the regional variability, which is the same map of this one, but we removed here the global mean trend of 1.76 millimeter per year. Another interesting point of doing ensemble mean reconstruction is that we can have an estimate of the uncertainty by computing the spread around the mean in the ensemble. That's what we've done here. And you see that this uncertainty lies between 0 and 1.5 to 2 millimeter per year, except in the regions of high temporal variability, like the western current boundary regions. Now, thanks to the reconstruction, we have an idea, thanks to reconstruction, but we can also use models. But here I will show you results with the reconstruction. We have an idea of the past sea level changes at regional scale in different regions of the world ocean. The point now is we want to estimate the total relative sea level rise in some places of interest. What we call places of interest are actually places which are known to be vulnerable. And I will give you here a few examples. We'll look at how we can compute the total relative sea level rise over the past decade in the Pacific Ocean, which is known to be vulnerable because there is lots of small islands and low-lying islands. We'll look also at the Indian Ocean. We'll look at the Caribbean and in the South China Sea. So it brings me to the second step of this presentation. How do we proceed now to compute the total relative sea level change? To compute the total relative sea level change, as I told you before, we need first the sea level change at the coast, which is the sum of the global mean sea level rise and the regional variability. And these two terms are given by the reconstruction. For example, they are given also by models. For global mean sea level rise, it's slightly different, but we can talk about this later. These two terms are changing, have natural variability, which is coming from ocean circulation and from climate variability also, but there is also a human-induced variability, essentially from the global warming. We often call this term as the climate-related sea level change. There is this other term, which is the vertical crustal motion, which gives the motion of the crust at the coast, and which we need to add to these terms to have the total relative sea level change. This term is essentially can be due to natural or anthropogenic factors. Natural factors such as sediment load, tectonic volcanism, as it was shown before in the presentation just before. But it can be caused as well by anthropogenic factors such as groundwater pumping or oil extraction. Today, we only have models to model a part of this, which is a part of GIA. I forgot to mention GIA in terms of the natural factors that induce vertical crustal motion. The only way we have to estimate the total vertical crustal motion in some places of interest is to use GPS devices or DORIS devices. And that's what we will use in the next slides to show you how to compute the total local relative sea level rise. So how do we proceed? Let's take the example of the Western Tropical Pacific. I plotted here the trends shown by satellite altimetry over the last 20 years in the Western Tropical Pacific, and here you see the trends from the reconstruction based on DRACA. The first thing we need to know when we want to estimate the total relative sea level change in such a place is to find out first the reconstructions that perform best in this region. I've plotted here in little stars the tide gauge records that were used for the reconstruction. The first thing we do is to collect every bit of tide gauge records we can find in this region. They are shown here by the black dots. For each bit of tide gauge record, we compare it with the different reconstructions to find out which is the one which is performing the best in the region. So you can see here in red the bit of tide gauge records we find for each black dot that we had on the map. And you can see in blue the reconstruction. This is the reconstruction based on the DRACA model. I've added as well the sea level measured by satellite altimetry over the last 20 years. So when we do this comparison, we end up with a reconstruction which seemed to be the best for the region. In this case, it was a DRACA-based reconstruction. Oh, there is a problem here. So when we have a reconstruction, we deduce from some places of interest. Here, Funafuti, Numea, Papit, the sea level rise over the last 6 decades. You have in blue the sea level rise measured by satellite altimetry over the last 20 years, and in red, if available, the tide gauge records at the places of interest. So now you will have to believe me, but actually I wanted to show here a map where, not a map, an histogram where we have the sea level rise given by the climate-related sea level rise given by the reconstruction for many places of interest in the Western Tropical Pacific. What it shows is that basically when we look at 6 decades, the climate-related sea level rise, which is experienced by most places of the Western Tropical Pacific, is close to the global mean sea level rise, except for a few places like Funafuti in particular. What is interesting is that when we use the GPS measurements to estimate the vertical crustal motion, we found here 9 places where we had a measurement of the GPS. Actually, the picture is fairly different. Now, the total relative sea level rise that are experienced by the places where we have added the vertical crustal motion computed with GPS is significantly different in general from the global mean sea level rise of 1.8 millimeter per year. So it's still a bug here, but anyway, here it was written 1.8 millimeter per year. So what does it mean? It means that actually the vertical crustal motion is an important factor for the total relative sea level rise. And when we add this factor, in general, we have a total sea level rise that ends to be significantly different from the global sea level rise. In the case of Funafuti, Funafuti experienced a climatic-related sea level rise of 4 millimeters per year, and now when we add the vertical crustal motion, we get to up to 5 millimeters per year over the last 6 decades, which is pretty big. We've done a similar study with the Indian Ocean, and you can't see the figure, but anyway. In the Indian Ocean, actually, the reconstruction that worked the best was the reconstruction the mean reconstruction, and it showed something which was similar to what you didn't see before, which is basically when you look at the climate-related sea level rise over the last 6 decades, you have a local sea level rise which is quite close to the global mean sea level rise. But when you add the GPS measurements or Doris measurements for the crustal motion, you see that some places now have a significantly different total relative sea level rise than the global sea level rise. Now, I'm afraid of the next slide. No, this one is a good one. So it was kind of these pictures before for Western Pacific and Indian Ocean. So we've done a similar study for the Caribbean Sea. In the case of the Caribbean Sea, we couldn't find GPS measurements or Doris measurements, so I only plotted here the climate-related sea level computed from the reconstruction. It turned out to be the mean reconstruction, once again, which performed best in this region. And you can see here clearly, it was almost the same for the other two previous slides, that when we look at the climate-related sea level rise over the last 6 decades, most of the region have experienced something which is locally very close to the global sea level rise of 1.8 millimeters per year, except for 2 places here, Gibraltar and North Sound. For the South China Sea, we did the same study. In the case of the South China Sea, we couldn't find GPS measurements because they are not available, actually, because China authorities wouldn't release their GPS measurements. But what is interesting in the case of China Sea is that we found out that the different places on the southern China coast and the western Vietnam coast have experienced a climate-related sea level rise which is significantly higher than the global mean sea level rise over the last 6 decades. And this is due to an enhanced warming of the China Sea over the shelf here, along the China southern coast. This is interesting because we know that some places here are experiencing a subsidence, at least Hong Kong here. So if we can have here GPS measurements, we surely will find that the total relative sea level rise is much higher than the global sea level rise over the last 6 decades. And this would be interesting to see what impacts this brought on the coast. Now, in conclusion, as you've seen, we are now about to estimate the total relative sea level rise in some places of interest. We didn't estimate it in that many places, and the first reason is because we are lacking GPS measurements or Doris measurements. So the first thing we would need to improve our results is either to instrument more places or to find more GPS measurements, especially in China, for example. The second direction in which we could improve is to improve the reconstructions, and there are several ideas to improve the reconstructions. We could use more tide gauge records if we have better high-quality tide gauge records, but also perform an ensemble reconstructions based on a bigger ensemble. The idea here is to follow on the work that was done, the first step that was done with the small ensemble mean reconstruction. There is also a need to perform regional reconstructions in some regions like the Mediterranean Sea or the Arctic Sea that cannot be covered by EOFs computed over the global sea level, over the global world. Thank you.